And I think we have done few questions on perturbation theory. So now the topic that we are going to start is application of perturbation theory, which is very important. Application of perturbation theory. As you all know, perturbation theory it is an approximation method which we apply to very complex systems, like for multi-electron system. So today we are going to apply this perturbation theory to helium atom. You know, helium atom is multi-electron system. In helium, how many electrons are present? 2 electrons, right? So the presence of the second electron, it disturbs the system. That's why we need perturbation theory. Okay. If we compare helium atom with hydrogen, you know, in hydrogen there is one nucleus and there is one electron, right? So only one type of interaction takes place between these two charges. That is known as attractive interaction. Okay, which is responsible for the potential energy. Suppose V1. Okay, and that is equal to ZE square upon R. What is R? R is the distance or the radial distance between electron and nucleus. Okay, but in helium atom, if we look at helium atom, we have 2 electrons. This is the nucleus positive charge, and we have 2 electrons. This is E1 and this is E2 having negative charge. So suppose electron 1 is present at distance R1 from the nucleus and electron 2 is present at distance R2 from the nucleus. Okay, and there is interelectronic distance also between these two electrons. Let's suppose this is R12. You can see if you compare hydrogen atom with helium, this is helium. So here we have one extra electron, which is E2, which disturb the system. How it disturb the system? The presence of second electron, it causes the interelectronic interaction between electron 1 and between electron 2. Okay. So there is a new type of interaction. So first of all, let's see how many type of interactions are taking place in this system, which will be responsible for potential energy. So in helium atom, is my voice audible?
Yes, ma'am.
Okay. और साथ के साथ नोट्स बनाते रहना, ठीक है? Okay, so in this system, 3 types of interactions takes place. 3 types of interaction. First is the interaction between nucleus and electron 1. Second type of interaction is between nucleus and electron 2. And third type of interaction which perturb the system is the interaction between electron 1 and electron 2. So we have 3 type of interactions which are responsible for potential energy. Okay. So from first kind of interaction, the potential energy that arises is equal to, you know, potential energy is the product of charges divided by the distance. You know, the charge on the nucleus is Ze, right? And charge on electron is minus E. Divide by its distance R1, you will get minus Ze square upon R1. So this is the potential energy arises from first kind of interaction. Similarly, second potential energy term arises from second kind of interaction, which is same minus Ze square upon R2. Student, please mute yourself. किसका अनम्यूट है? Okay. So from third kind of interaction, we get a new potential energy term, which is E3, and this is equal to, what is the charge on electron 1? It is minus E. Charge on second electron, it is minus E, divided by the distance between them, it's R12. Okay, the product will be equal to positive E square upon R12. So these are the three kind of potential energy. So out of these three, two are attractive in nature and one is repulsive in nature. So first two interactions, these are attractive in nature. These are attractive in nature. That is why the potential energy is negative. Okay. And the third interaction, it is repulsive in nature. Why? Because it's happening between same charges. So it is repulsive in nature. Repulsive in nature. Okay. Because repulsion always makes the system unstable and energy increases. So that's why here potential energy is positive. This is repulsive potential energy, and this is the disturbance in the system. This is the actual disturbance in the system that arises due to the presence of second electron in the system, in helium system, or in the system. Okay. This disturbance in the system, in any kind of system, it disturb the Hamiltonian also. If the Hamiltonian changes, the energy also changes. Okay. So in application of perturbation theory to helium atom, we are going to find the perturbed energy. Okay. So, to find out energy, we need two parameters. Wait. Yes. So to find out the energy, we actually need two parameters. What are these two parameters? Can you tell? What are the parameters that are required to find the energy of any system? To find energy, we require or we need two parameters. First parameter is we require Hamiltonian. The Hamiltonian of the system should be known to us. And second is wave function. It should be known to us. If we know the Hamiltonian, if we know the wave function, then this Hamiltonian, it will apply on this wave function and will provide you energy as per your eigenvalue equation. Okay. So our main task in this helium system is to find out Hamiltonian, and then we will find out the wave function. Okay. So let's find out what will be the Hamiltonian of helium system. Hamiltonian is sum of kinetic energy and potential energy, right? What is Hamiltonian? It is the sum of kinetic energy and potential energy. Okay. So how to write kinetic energy of the system? What is kinetic energy? It is P square by 2m, right? And potential energy is, now in helium atom, we have three types of potential energy terms. So here you will write V1 plus V2 plus V3. Okay. And P is your momentum by 2m. So let's find out the kinetic energy term. P is equal to minus iota h cross curl by curl m, curl by curl x, and P square will be equal to minus of h cross square curl 2 by curl x2. This is for px. Similarly, we will be having p square y and p square z. Okay. So your Hamiltonian for helium atom will be written as, here we have minus of h cross. That will be common in every term. Okay, divided by 2m. And here we will be having, see, we have 2 electrons. Okay, we have 2 electrons in helium atom. So we will write the kinetic energy term for first electron, and then we will write kinetic energy term for second electron. Okay, you know, we represent this term with del 1 square. Okay. So here we will write del 1 square plus del 2 square. What is del 1 square? It's a Laplacian operator for electron 1, and del 2 square is the Laplacian operator for electron 2. Then we will write potential energy terms. V1, which arises due to interaction between nucleus and first electron, and it is equal to minus Ze square upon R1. And second potential energy, again it is negative minus Ze square upon R2. Third potential energy is positive, which is E square upon R12. Okay, this is the Hamiltonian for helium atom. Is it clear? Yes, students?
Yes, ma'am.
Okay. Is it clear why I have written del 1 square and del 2 square? You can compare the Hamiltonian with hydrogen atom. Okay. For hydrogen atom, how we write the Hamiltonian? Because hydrogen is a one electron system. So if there is a one electron, how to write the Hamiltonian? Hamiltonian is equal to minus h cross square by 2m, simply del 1 square, plus potential energy. And potential energy, it was equal to Ze square upon R. Okay. So if we have one electron, we will write del 1 square. If we have two electrons, we will write del 2 also. Wait. Okay. Now this Hamiltonian, or we can say this Hamiltonian, it contain two parts. Okay. So first is the unperturbed Hamiltonian, and second is the perturbed or the perturbation. So you can see, student, this meeting will end in 10 minutes. You have to rejoin. Okay. So this Hamiltonian, it contains two terms. One is H naught and second is H dash. What is H naught? H naught is the Hamiltonian for unperturbed system. Okay, and H is the perturbation or the disturbance. Okay, so this H dash or the disturbance or the perturbation in the system arises due to inter-electronic repulsions. Why it arises? Due to inter-electronic repulsions. If we remove the inter-electronic repulsion term, we will get the Hamiltonian for unperturbed system. Okay, so let's see in H which part is for Hamiltonian for unperturbed. This is the part. This is the Hamiltonian for unperturbed system, and E square plus R12, this is H dash. This is the perturbation in the system. Okay, so here we will write it separately. H represent perturbed Hamiltonian. Perturbed Hamiltonian. Okay, so H naught, which is the unperturbed Hamiltonian, it is equal to minus H square by 2m del 1 square plus del 2 square minus Ze square upon R1. minus ZE square upon R2. Okay. And perturbation or the disturbance in the system, it is E square upon R12. Clear? So student, we can write this Hamiltonian, these three Hamiltonian in atomic units also. In atomic units, in atomic units, in atomic, sorry, in atomic units, we take H cross or A naught or mass approximately equals to 1. Okay. So in the expressions of Hamiltonian, we will put H cross A naught or M, these parameters equals to 1. Okay. And we are doing this derivation for helium. So, you know, for helium, Z is equal to 2. So everywhere put Z is equal to 2 and these three parameters equals to 1. So let's write. Wait. Let's write H. So H was equal to minus H cross square by 2m. So we will write 1 in place of H cross square and by 2. Okay. Into del 1 square plus del 2 square minus Z is 2. 2 by R1 minus again Z is 2. 2 by R2. Only the distance is different. Then plus E square. E square is also 1. 1 by R12. This is the Hamiltonian for helium system. H cut की value 1 कैसे ली? Okay. We take all these values approximate 1 in the atomic units. अगर atomic units लेते हैं, we take all these value equals to 1. Approximately equals to 1. Okay. Then we will write H naught. H naught. So you know H naught is this part. Minus 1 by 2 del 1 square plus del 2 square minus 2 by R1 minus 2 by R2 and H dash, which is the perturbation or disturbance in the system, it is equal to R12. Okay. So you can mark these equations as 1, 2 and 3. Is it clear? Yes, students, any doubt?
No, ma'am.
Okay. So as I told you in the starting of this article, to find the energy, two parameters are required. First is Hamiltonian and second is wave function. So Hamiltonian we have found that this is the Hamiltonian for helium system, which consists of two parts. One is unperturbed Hamiltonian and second is the perturbation. Okay. And sum of these two will give you the Hamiltonian of helium atom, right? And one thing more you can notice that in case of H naught, means in equation number 2, this is equal to sum of Hamiltonian of two hydrogen like system, right? Of two hydrogen like system. Can you see? Your H naught, it is the sum of the Hamiltonians of two hydrogen like systems. So we can write it as H naught 1 and H naught 2. Hydrogen like system means one electron system. Okay. So H naught can be rearranged or can be written as H naught can be written as, see, if we have only one electron, how to write the Hamiltonian? We write minus 1 by 2 del 1 square and its potential energy, right? This is the kinetic energy of one electron. This is the potential energy of first electron. Okay, then we have second hydrogen system also. For this, how to write the Hamiltonian? Again, minus 1 by 2. This is for second electron, del 2 square, minus 2 by R2. Is it clear? Now, this is the Hamiltonian for second electron. It corresponds to kinetic energy and second term corresponds to potential energy. Is it clear? Yes, students? Any doubt? You can respond in your chat box. Okay. Your meeting is going to end in 2 minutes. Okay, students. So the unperturbed Hamiltonian, it is actually a sum of the Hamiltonians of two hydrogen-like system. Okay, that means we can write, we can apply Schrodinger equation to the unperturbed system, right? So here we have found Hamiltonian. Now we will try to find out the wave function. Okay, how to find the wave function? Let's see. So here we can consider that your helium atom, it's a two electron system. Okay, it is a two electron system. Electron 1 and electron second electron. It's a two electron system, or E1 E2 we can write. You can write E1 and E2. E1 and E2. Okay. So we can further consider that your helium atom is supposed to be like two hydrogen-like system. It consists of two hydrogen-like system, because in hydrogen there is only one electron, but in helium we have two electrons. So we can consider it as a two hydrogen-like systems. Okay. So we know the wave function for hydrogen atom. So we will try to write the wave function for helium atom by assuming that this system is equivalent to two hydrogen-like system. Okay. So wave function we will write, because your meeting is going to end, we have to rejoin. After that, we'll let you know.